divide for talking about how the Taylor series does the Taylor series work. I apart it to 3 parts. So and today let's going to talk about the first part. And so first we're gonna so let's think about a function. This function is called 1 plus x squared, and this is the original function. So now we can draw out a picture, and it will calculate so the intercept is 1, and we can write it like this. Good. And we just calculate to this bar like this. So now we're gonna focus at 0. So to the last video we talked about a Taylor series here. So first now the Taylor series of this function is still a self. If we focus at 0, this is our original function, and its Taylor series is 1 plus x squared. Now let's see first. So there's one problem right here. So we actually know how do we write this function. So the first term is 1 because we plug in because we plug in 0 in this function, so we have 1, and then we plus, so we have a 1 over 1 factorial, so it's 1, and there's so the derivative function of this guy is 2x plus 1. If it's 2x plus 1, so we have this, so we plug a 0, so it's 1, and then we just times x. Good, and then we plus another thing. So this guy's third derivative function, this guy's second derivative is what? This guy's second derivative is 2. Right, it's 2. So if it's 2, then we just we have in the front we have a 1 over 2 factorial. So if we just sum together, so it's 1, and we have another x squared, so it's like this. So okay, so first let's see the first 1 right here. This is we can imagine because we just plug in 0 in this picture, so we have this value, and with this value, so our aim is to find, if we plug in 1, this value. So this is the problem. So how do we calculate this? So first we have it in the step right here, right? We cannot say it in the value. Good. And the second is x. Actually, we just should rewrite it as 1 times x, and the 1 is the speed right at this point. If we just plug in 1 here, good. Sorry, the speed if we plug in 0, so it's this. Okay. So this value is 1. If we plug it in, so we know this is a 1. Good. And okay, so now we have another here is 1, so we just plus it to 3. But the problem is, what is the picture of here? So we need to draw this function's derivative function. Actually, it's you see, if we just have this, you see, its derivative function what? It's 2x. It's 2x plus 1. So 1. Okay. 1, 2. 1, 2, 3, 4. Good. Good. And so now this right here, this value right. So this value right here, we know we just plug in 0 in this function. Good. So in this, if we just plug in this function, so but if we, and of course this is the differential function of this function, this function. So this is 2x plus 1. Good. And so the problem right here is let's think. Okay, so what's the area right here? So you see, if we plug in 0, there's no area because the time is from 0 to 0. So we don't have even an increment. So we don't have it. We don't actually have an area here. We will talk about later why is this. So so first, this is 0. Because we can't see this in the differential function. So let's see the next part. It's 1 times x, right? Sorry, I drew this wrong here. It should be we start from 1 because we have the intercept 1. So good. Good. So we're like this. So right now. So first, so of course it's the same. This term we can't see this, and we can't see it. So and this term you see it's 1 times x, and 1 is a speed. I mean the value right here. If we plug in 0, of course in this picture we just the speed right here, right? Right here, the speed is 1 actually. The speed of this point is 1. Good. And so right here, so the speed is right here. So which time is the x? So we have this rectangle. And this is the area. Good. And the next step, and this term is the second derivative of this function. Of this function. So if it's of this function, the second derivative, you see, because right here, every value, you see, because we just, all of the values right here, because all of the numbers meaning here is some value, because we just, first we have the value and we plus some values and then just infinity approaching the last number. Well, this is, in this time, this value we just can calculate out. So it is not infinity approaching, just 3 times and we can just have the number. And so right here, so if we just, and right here, the problem is right here. So we think about this term, so it should be the second derivative. It's 1 and then times x squared. So what it's the second derivative should be 2, and we just times another 1 over 2. That's why. So and so we know this because you see x squared. So if we just draw, we just use the speed right here. So 2, but actually we shall draw a derivative function. So we just from 0 to 1, and then, well, of course, the 1 shouldn't be here because this one is 2. So just like a half. Just this, okay. Just this area. Good. If we add this area, so that means right here is this value. So we know actually right here, the speed right here, 2, we can write it as this over this. And we just times it this, so we have this. And we have this. Then we times another x, and 1 over 2. So we have this area, right? So we just so we have this area now. That's why. Okay. So now we have this area. So this is the value right here. So of course now the problem is why we can't see the value of 0 right here. So of course we think about, so if we can write some any functions, if it's integral 0 to 0, so the answer of f of x maybe, and dx. So this answer is 0 because you have f of 0. Sorry. Okay, so you have the derivative function of f of x. And then here's f of 0, and minus f of 0. Something like this. So what do you have? It's 0. So if you integrate like 0 to 1, so you in f of x minus there, f of x, derivative of f of x, and then dx. So you have f of 1 minus f of 0. So you just have a value, right? So just this value. So the problem is, even if you integrate, so let's think about another thing. What is the definition of the intercept in the original function? It is if we plug 0 in this original function, and we have a y value, and this y value is the intercept of y. So, and this number, so the problem is in the derivative function, even if we have an area, right? But only one thing we can't see in the derivative function. What is it? It's the intercept. We can never see in the derivative function. That's why. So actually, even if we have an area right here, we need to write it as, so if we just write the area in this derivative function, this area should be the true area minus the intercept. Okay, so now let's continue to think about, if it's, we call this focus 0, calculate 1, because we just focus at 0 point and we just calculate the value of 1, right? Focus at 0, we just focus at 0. So the next step is to calculate the second. So the next, of course, we're going to calculate 2. So we can focus as 1. Okay, just not really good. So let me try it again. Okay. This is 2, and this 1, and 4, 5. Good. Okay, this is 2, and so this is 3, and so I draw much higher. Good, and we have 6, 7, 8, 9. Good, and so you see here it's 4 plus 2 is 6, and okay, it's 7. 3, 4, 5, 6, 7. Good, right here. And so on. I don't draw that much, okay? So just finding something like this. So if we focus at 1, we can write it 2. So the first one is this function of 1, right? So if it's this function of 1, so what's that? It is 3. So it's 3 plus, and of course, if we just derivative it, it's 2x plus 1. So we have, if we plug in 1, so we have 3. So it's 3x. Sorry, because we should write it as x minus 1, right? I told you why later. Okay, and then plus another thing here. It is, and we have 2. So we just have x minus 1 squared, because don't forget here, we have a 1 over 2 factorial. So right here it's x plus 1. So the problem, because we're going to talk about the picture, so we need to write out everything here. So it's 1 over 2 factorial, and then we have a 2 times 2, and then an x minus 1 squared. Good. So we have the value here, and so this one is the same. Let me just draw it again, okay? Good. So first, the problem is first we have the area right here. Right? Good. And this is 3 minus 1. Good. And right here it is, first we have this value, and the first value right here is this, and this is 3. Good, and then next one. So next one is, we have a line right here, and the next one is 3. And then, this 3 is the speed right here. So it's this right here in the original function here is the speed of 1. So, but we have the speed. So we actually can write it as value like this. Okay. Good. Okay. Okay, so right here it means this rectangle, right? 3. Alright. This is the value right here. Good. So now we have this area. So this area now, yeah, this is this part. So and this part, of course, right? We can think here. So first it's 2. So right here we know this triangle. We actually are going to calculate this area of this triangle, and we know this is a triangle. So actually the function of this triangle right here, this line is it's a linear equation. So we're gonna write. So we just draw the derivative of this function. Constant, right? And this is 2. And the point right here is first we have 2. And then we calculate the area from 1 to 2 because it's 2 minus 1. So we calculate the area right here. Good. So then we calculate the area right here. So this area means this value right here. We know actually 2 is the speed right in the point 1. So we can right here, so we can write it as this over this. This over this. So right here is, what is this? So this is okay, so first 2 times x minus 1, right here is this high, and then we times another x minus 1, and times 1 over 2, so we have this triangle's area. Good. Okay, so that's how we find the value right here. So, okay, so, actually, we can compare these two. First right here is 0 to 1, and right here is 1 to 2. So if we compare it, so right here, we actually the difference is right in the first term. You see if it's 0 right here, so the first term right here is what is, so we don't have intercept right here, but and if we focus at 1, so we have a value right here. So, but the problem is, even if we have a value, that value actually is 2, not 3. We just because we can't include, because we can't see, and right, we can't see the intercept in the derivative differential function. Good. So we don't see the intercept, so we only can find 2 right here. Good. And so actually, if we want to find the value of 2, we also can calculate from 0 to 2. So let's draw the derivative function. So first, now you know how to solve this problem now, right? First we have this area, because we use this value to time this. Good. And the next thing, of course, is 1. So now we just have this one. Right? Because if we just... Okay. So we have here it's 2. No. This is 2. So it's the same. 2. Good. So we just found an error right here. Good. So right here is this value, and then we times this and then 1/2, so we have this. Okay, so we have to solve the problem with 1 plus x squared. So now let's talk about e to the x. Great. So now I gotta solve this problem. So first, now we know. So now we already have the experience from thinking about the problem of 1 plus x squared. So let's talk about e to the x easily. Well, the problem is the third term. We don't have the third term right here because this is a quadratic function. We don't need to have that, the third term. The quadratic equation, we only need to have 3 terms. Okay, we solved the problem. But e to the x, it's exponential function. So it's not some power function, just x to what plus x to what plus x to what, something like that, and the power functions. So it's not like this. So it's a different function, right? So good. So first, this is the Arduino function. Good, this is 1. Okay, so first let's rank. Good, so we focus at 1. Okay, so I focus at 0. 1 plus, okay, it is 1. Good. So because we have the value, so we can draw the picture beautifully. So first, let's write out the values. Okay. So first it's 1, and we plus. Let's think. It should be 1 times x. And then the next one is 1/2 factorial times 1 times x squared. Good. And we plus. Good, okay. And it's 3 factorial. And 1. And next to the 3. Good. Okay, good. Okay, so, and then infinity so on, we don't need to talk about other terms if we know how to solve this term. So first, let's think about it. We just calculate 1, right? So first, the first value is 1, and the second value, the second value right here is if we calculate it is 1. Good. Okay, so right here in this term, it is 1/2. Good. Okay, so So, good. Let's think. So right here. Okay, so first we had this value. Okay, so let's think about the derivative function. Okay, so first we have this. And second we have and then we have okay. Good. Okay, so the problem is right here. So first this one, of course you know this part, and this one I mean this part. So this part, let's think. If we write it out, so first we have 1 and we times x. And then bracket. And then we times another x and then 1 over 2. And we times x and then 1 over 3. So what happens here? You ask, hey, what are you doing? It's strange, right? So here, this is actually 3. So right here, we're gonna think about the function right here because you think this is equal to our original function, and our original function picture right here, and this is the derivative of our original function. If we draw the functions right here, not the areas right here. If it's the area right here, just this. But we're gonna think about the functions. So we shall derivative this guy too. So we have the functions here. So this term is this term. So this term we need to derivative it. So we just have this function, and we know this is a quadratic function. Good. If we have a quadratic function, right here, so we actually know right here, we actually, because you see, we just have a value right here, it's x, so like this, so we just have, we can project it like this. We project this from this to... Of course, I forget to say something here. So if we just have some here. So first from this part, you see, because this part, you see the slope is the slope of point 0. So, you see, and from this function, we know where the slope is from point 0. So the next term we can't touch we cannot still use the point, the slope of the point 0, but we can use the slope from the point 0 plus the x, and the x is inside delta. So if it's inside delta, so what we have inside delta, so we can't see, but it exists, right? Good. So it exists. So we just, right? So okay. So now let's keep on. So here we project. This is a straight line. Good. Okay, this projected this, and this is a quadratic function. So right here. So first we need to have this, and this is this function's second derivative, constant. Right here it's from 0 to 1. And then next, so this means this guy's first derivative. Okay, 0 to 1. And this area means this value. And this is because this one, so first this one is right here. We times this, so we have this area. And this area means this value. Okay, means this part. And this value when we times x and times 1 over 2, so we have this triangle. The area. Okay, so this is this. Okay, 0 to 1. Okay, so right here, this one means this one. So if we want to calculate the area right here, of course we times 0 to 1. So what we have here. Okay, so, and we times another 3, 1 over 3. So we have this. So why is 1 over 3? Because normally, if we just have an integral, so we have a function, and then let's do this 3, and then we differential it, so we have a quadratic function, so it's actually 2. Okay, good. Okay, so if we want to calculate maybe 0 to 1, and this value, the value of 1, and so here is this area. So if it's this area, so if we just have if we think the function is we use the speed right here. So of course, its derivative is 3x squared. So right here, we just use the speed to times another x and then 1 over 3. So that means this area is 1 over 3 of this rectangle. Good. Right here, that's why. Good. So we have this, so we know how to calculate out this. Good. So actually, okay. So now we had this. So actually right here we can calculate from 1 to 2. Focus 1, calculate 2, and this one is focus 0, calculate 1, right? Okay, this is the value. Okay, and so the second derivative. Okay, so I've gotten the second derivative. So first, right here, what do we have here? If we write it out, it's e to the 2. E to the 1. E to the 1 plus e to the 1 times x plus 1 over 2 factorial, and then times e to the 1 times x squared, and then plus 1 over 3 factorial, and then times e to the 1, and then times x to the 3. Good. So we're right out here. Okay. So this is e to 1. And put it 2. Good. So the first value is right there, here. Good. Okay, So right here, okay, let's draw its derivative function. So of course right here, so first we have this value, so and then right here we just use speed 2 times this one, and we have this one. Okay, so let's draw this here. Okay. So first this area right here. So no, this area we need to, and this area actually means e to the 1 minus 1. Okay. Good. And so, okay, so next step right here is we use e to the 1. Okay, so this rectangle right here. Okay. And so the next one, like this. Okay. First term is this area. And the second term we use is 1 times x. Sorry, okay, sorry. Here should be x minus 1. So it's x minus 1 here. And it's x minus 1 here. Good. Okay. Let me see here. So, okay. Let me use black one. So first we have e to the 1 and times this one. Actually, is x. This is actually 2. Just write x and this 1. And so we just times x minus 1. So we have this area. Good. And this part. So right here, of course, we know e to the 1, and this is x, and this is 1, and we just calculate this area, and this area, this value, and then we just have in this one, and the 1 over 2, so we just here. Okay. That's right, this part is also the same. Project it like this. Good. And so first, and it's 0 to 1. Sorry, it's not 0 to 1. It should be 1 to x. Good. And so first, this one is e to the x, and we just time this one, x minus 1, so we just have this area. Good. And we want to calculate the area of this triangle. Then we just times another x minus 1, and then we just times 1 over, then times 1 over 2, because this area means the height right here. 1, 2x. Good. Okay. Okay, so right here is 1, 2x. Okay. Okay, you know, right? Okay. So this is the part of ETX. So the last part right here, we're going to talk about x plus x squared. Good. And if we talk about x plus x squared, so let me tell you what this function looks like. Okay, so this is 1. So 1, 1, 2, okay, 2. Good. I'm plugging 0, 0. So it's intercepted 0. Good. And if you calculate the least value right here, I mean the lowest point right here, okay, this is 1, this is 1, this is 1, okay. And this one, the negative 2, negative 2, negative 4. This is a little point and okay. Okay. Good. So now let's think. It's derivative function. We just think about it if we focus at 0. Why it's special? Because let's think if we focus at negative 2. Sorry, negative 1 over 2. This is negative 1 over 2. And this is 1. This is negative 1 over 4. Don't write it. So let's focus at negative 1 over 2. Good. 1, 1. Okay, and this one's a derivative function is the first derivative function is 2x plus 1. Okay, so right here it's good. Okay. So we're gonna find this part. Okay, so we know we have a value right here. If we write out how to write a negative 1, we focus on negative 1 over 2, and we calculate 1, so it's f of 1 over negative 1 over 2. And then plus f of 1 negative 2. I've got the derivative, first derivative, and then x minus 1 over negative 2. So negative 1 over 2 and squared. And sorry, g1. So just write this. And we plus, plus 1 over 2, okay, to 2. Good. So when you match here, so we have something like this, and this is 2. 1. Alright. Do a -2. Something like this. Good. Okay, right here. So here, this part is 0 because this one, if we just plug it in, it is 0. Good. So we just think about this part and this part. So if it's this part, we have it here -4. But you see, -1/2. So we don't have the value of -1/2 right here. We can't see it. This is different. Maybe it is because we just chose negative. It's different because you see, because we just chose, because we chose -1/2 here. So right here, because the speed right here is 0, so we just have the value 0 here. So we don't have the area right here. We don't have the area right here. So of course. And we plus this part. So this part actually, if you calculate, you will find out is this whole big triangle. And of course, this little triangle is positive, right? It is positive. So what I'm going to do now here, this whole thing is positive. So problem we can imagine right here. This positive part, mapping right here, is like this. To here. From here to here. This positive part. And we must need to go back to this picture. So we have a -1/4. So this is negative, right? So we just cancel out this part. So we just have the part right here. So that's how we find the number. Right here, let me remind you this place again. So let's think. Because you see this function, right? So we have something like the least value right here, and we have a value right here also. So maybe we just have 2 values like that. So but in math we only got to start here. We can say we're gonna research how does it behaviors. So the problem. So right here we can think of this function. In this function, you see we have some values like this or this, and we even can find every speed right here. Right here, just something like this over this, 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 something like this. So, and also even we can find the total increment right here. So we can just, you see, the areas right here. So it's just like here. You see, here, just some values right here. Just the values right here. Okay, so this is what I'm gonna remind you right here. So this is the first part of how does the Taylor series works. So this is we can say this is chapter 1, and so this is today's video. And I just add something right here in the last video. So in the last video, I just talked about, you see, let's think about this term. I mean the fourth term right here. So in the last video, first we know this is a constant function, and we just, because this is the third derivative, right? And we're just integration it back. So in the last video, we say it's integration. So if it's the definite integration, so we just calculate about the area. It can say means right here just a value. But actually, we think about the indefinite integration. So that means we can have some slope right here. We can have some slope right here. Just some slope, some different slope right here. And they respect their own x value. So we have infinity tiny increment. So we have a value. And we have infinity values. So they create a curve. Then the curve can move in the space because we have a plus c. But the problem I want to talk about right here is, what about the speed of point A right here? Just the point right here, and it's the neighbor with A. We can say it's a plus dx. It's neighbor with A, and it's the nearest with a, and so we can say the speed is because a 0.8, it's just really 0.8, so the speed is equal to 0. So it's nearest to 0. The speed is nearest to 0 right here, and we're just getting bigger, and we just have these slopes. And so another thing I want to talk about right here is you ask, so this term, this is a fourth term, right? You see this one in the picture, you see the base is flat. So what you're going to do is just project right here, so we can think about the slopes problem, something like this. And you will ask, so what about the fifth term? Because the fifth term is just a cubic function, right? Like this, you see. I have this. And the base is also a curve. Actually, it's a coordinate function. Right? The base is also a coordinate function. So what do we do? It's fine because we also can project it to horizontal, so we can think about this problem.